Good day, students. My name is John Ogodo. Once again, today we want to look at the topic, calculus. Okay, we'll be considering this topic, calculus, based on two major aspects. And this major aspect have to do with differentiation and integration. Okay, so we'll quickly look at the term calculus in our basic language. Here we are going to be looking at the introduction, how calculus was developed briefly. I'll just describe brief historical view on that. Then we talk about differentiation or differential calculus and its applications. Then we look at integration or what we call integral calculus and its application. Okay, so basically the history of mathematics present the development of calculus has been accredited to Sir Isaac Newton, 1642 to 1727, an English physicist, mathematician, and Gottfried Wilhelm Leibniz, 1646 to 1716, a German physicist and mathematician. The introduction of calculus created an explosion in the development of physical sciences and other areas of sciences and mathematics. Calculus forms an integral part of the mathematics for high school and college students and the universities, okay, in our everyday life. So it's an interesting branch of mathematics. Okay, so we are going to be linking calculus to a lot of areas of application. And basically, we say that calculus is the rate of change of a quantity with respect to another, as from basic definition. But before we look at the holistic view of the term calculus, let's begin with what we call limits. Calculus is the study of differentiation and integration. This is indicated by the Chinese translation of calculus. Both concepts of differentiation and integration are based on the idea of limit. So what is limit? The term limit comes from a function. When we talk about a function and we want to limit the variables or the extent to which the function can be varied or treated. So the term limit, if you are given a function, f of x is equal to y, and we're looking at the limit of the function. That means as the value of x approaches a particular number, let's say the number is approaches is a. That means what we are looking at here is the function of a. What is the function of a and what will it give with respect to y? So the function of a with respect to y will be a function in terms of y with respect to a. Okay? So we're just trying to use this to define the term limits. So basically, we are going to consider how we can solve problems in limits, and from there henceforth we'll move on to what we call differentiation using the first principle. Differentiation using the first principle. So basically, we have said that limit is the value of the x or a function when the values of the variables are substituted into a function to know the extent or the limit of the function. Let's consider something like this. We are given a function f of x is equal to 2x plus 1. And we want to limit this between the range x approaches 1. Therefore, we can just say that the function, how does this function, f of x, behave? We are given that f of x is equal to 2x plus 1. F of x is 2x plus 1. If we substitute the value of x equal to 1 in this equation, that means x equal to 1 from what is given, that means as x approaches 1, we say f of 1 is equal to 2 multiplied by 1 plus 1. So 2 multiplied 1, we have 2 plus 1, that will give us 3. That means the value of f of x as x approaches 1 is equal to 3. Okay? That is just the basic definition. With this example, we have been able to establish the definition of the term limit. We're going to look at more examples on limits and how the change is, the rate of change affects one value and the other. We're given a function there, x squared minus 9 divided by x minus 3. Certain limits in further maths or in mathematics, you need to simplify or evaluate the given function. when you simplify the given function, then you solve for the function. For example, you are given this, evaluate x, evaluate limit f of x approaches 3 of s squared minus 9 divided by x minus 3. What will this give? That means what we are looking for is the value of this function as x approaches 3, or we say as x tends to 3. So as x tends to 3, we say that limit of x tending to 3, that is x equal to 3, is substitute. If you substitute this, we have 3 squared minus 9 divided by 3 minus 3. The answer here will be 9 minus 9 divided by 3 minus 3. That will be 0 divided by 0. Let's say 0. But this will give us a wrong computation. But if we are going to simplify this, we assume this function that is given can be evaluated. So what we do is that the limit of x approaching 3 under this must be simplified. That means s squared minus 9 divided by x minus 3 can be simplified. And we have this using difference of two squares. We have 3s squared minus 3 squared divided by x minus 3. So when we simplify this, we have x minus 3 and x plus 3 all divided by x minus 3. So x minus 3 cancel x minus 3. So the limit of this function as x approaches 3 will be when you substitute x equal to 3 into the function. So our answer then becomes 3 plus 3. So 3 plus 3, the answer is 6. That means the value of this is 6 as x approaches 3. Very important, when you are given an expression to deal with and you notice that the expression can be simplified or factorizable, then you need to factorize or simplify the expression before solving the expression. Let's see another example when you are given simplify the limit. Let's see how we can simplify s squared minus 1 over x plus 1. Okay? For us to simplify this, we have x squared minus 1 squared divided by x plus 1. Okay? And that will be x plus 1, x minus 1 divided by x plus 1. So this cancels this. So if you have to simplify this, what about if you are evaluating? You are evaluating that same expression, evaluate as the limits of x approaching, in this case, let's say x approaches 1. If x approaches 1, s squared minus 1 over x plus 1, it is equal to, when you have simplified this, x plus 1, x minus 1 divided by x plus 1. And this cancels this once again as we have it there. So we have limit of x approaching 1, x minus 1. So the answer is 1 minus 1, and that is 0. But if we have to substitute directly into the expression, let's see what will happen. Second method of this. When you substitute directly, you have limit of x approaching 1, substituting s squared minus 1 divided by x plus 1. It is equal to 1 squared minus 1 divided by 1 plus 1. And that is 0, sorry, that will be 1 minus 1 divided by 2. And that is 0 divided by 2, and that is 0. So in this case, the two answers are equal. That means this one, there is no problem solving it in that two method or using that two method. But however, we may have it in terms of this, and you are having limit x tends to 1, simplify s squared minus 1 divided by x minus 1. In this case, if we simplify, we have x plus 1 and x minus 1, all divided by x minus 1. This cancel out with this, and what we have there is a limit of x approaching 1, x plus 1. So that is equal to 1 plus 1. And 1 plus 1 is equal to 2. So the limit of this is 2 compared to the other one we have earlier. Okay, so we have been able to establish that the limit of a function can be solved using substitution techniques. However, we can also solve them by simplifying them before dealing with other things that are also involved in examples of limits. So we have other limits. Find limit of x minus 1 divided by x squared plus x minus 2 if it exists. That means we are solving x minus 1 divided by x squared plus x minus 2 if it exists, as the limit tends to 2. So how do we do this? For us to do this, you need to solve directly. And when you are solving directly, as x approaches 2, we can say 2 minus 1 divided by 2 squared plus 2 minus 2. And that is equal to 1 divided by 4 plus 2 minus 2. And that is equal to 1 over 4. So we have 1 over 4 as the limit. If you look at the expression, you check, is it factorizable? If it's factorizable, can we factorize the expression? So if we can factorize the expression, let's see what we have. We have plus x here, we have minus 2. If you try to factorize this, we have 2x minus x. It's not factorizable. So the expression is not factorizable. Since the expression is not factorizable, what you do is that you substitute directly. If your expression is not factorizable, you substitute into the expression directly, or the given function directly. Okay, so we have considered limit examples. We have some examples or questions we can solve there, and let's see where we can add 1 or 2 examples based on some of the examples we have in terms of square roots and in terms of other related variables. So let's see additional examples. Like when we have evaluate limit x tends to 4, square root of 4, square root of x plus 2 divided by x minus 2. And that is for 1. And the second one is limit x tends to 1, square root of x plus 1 divided by x minus 1. Okay, x plus 1. For us to solve this, let's see how we can solve this one quickly. We have x here. Okay, we have x there. We have square root of x. So if you substitute x equal to 4 here, that is x approaching 4. That means we have square root of 4 plus 2 divided by 4 minus 2. So we have 2 plus 2 divided by 2. And that is 4 divided by 2. And 4 divided by 2 is 2. So the limit of that is equal to 2. However, the square root of 4 can sometimes be plus or minus 2. So here we are using the positive aspect. If we use the negative of that, negative 2 plus 2 divided by 2, that will give us 0 divided by 2, and that is equal to 0. So that means the answers can come in 2 ways if we are given that find the variables or find the values of this when the function, this root x plus 2 divided by x minus 2 is limited by x approaching the value of 4. In this case, we also do substitution because the expression is not factorizable. So we say that x approaches 1. So that will be equal to square root of 1 added to 1 plus 1 divided by 1 plus 1. Square root of 1 is 1 plus 2 divided by 2. So the answer is 3 over 2. Okay? But however, if the square root of 1, since the square root of 1 is plus or minus 1, because plus 1 multiplied by 1 is equal to 1, minus 1 multiplied by minus 1 is equal to 1. So we can also use the other method and solve and say this is minus 1 plus 1 divided by 1 plus 1. That is minus 1 plus 1. So that will give us minus 1 plus 2 divided by 0. And if you have this, that will be 1 divided by 0. And 1 divided by 0 is infinity. So we have an infinite answer. So this cannot, that means it doesn't exist. The number does not, the function does not exist when x is simplified as minus 1. Does not exist. Okay? So we can look at other examples that have been given in the slide that is shown on the board. We can solve those problems and also find the limit of those expressions. Okay, as we go along, we are going to look at the term differentiation. How do we deal with the term differentiation? Differentiation is another name for the term derivative. Okay, when we are finding the differentiation of a number, that means we are looking for the slope of a function, or what we call the gradient of a function. The term differentiation is very important when you are dealing with rate of change of a particular quantity with respect to another. Okay, differentiation is rate of change. Basically, you can say rate of change. Okay, rate of change of a variable with respect to another. With respect to another. So let's see a function. Y is equal to f of x. Y is equal to f of x is a function. And therefore, if that is a function, let's say it's a straight line. For example, here is your y-axis, and here is your x-axis. The function is this, represented as f of x. The slope of this is delta y divided by delta x. That means we can get the slope of this curve or this straight line graph by using slope is equal to x, that is delta y divided by delta x. And here can be taken we can take the value here as y2 and take the value here as y1 and take the value here as x1 and take the value here as x2. So when we find the slope of this or the gradient, we have y2 minus y1 over x2 minus x1. Okay? From the knowledge of geometry, coordinate geometry, if you are given the point, maybe you are given the point A, 2, 1, and B as 0, 3, and you want to find the slope between the 2 points, or the gradient. How do you find the gradient? The gradient, which is equal to the slope, is equal to delta y divided by delta x. And that is equal to y2 minus y1 over x2 minus x1. And here is your x1, here is your y1, here is your x2, here is your y2. So when we substitute these values into the expression, y2 is 3, y1 is 1, x2 is 0, x1 is 2. So when we subtract, we have 2 divided by minus 2. And 2 divided by minus 2 is equal to minus 1. So with that, we want to see how we can now solve problems in terms of curve. What will happen when there is a curve in this case? To find the gradient of a curve, that means you are looking for the rate of change of the variables, the independent variable and the dependent variable. If we are given that y equal to f of x as a function, that means that x, for example, y equal to x squared, this is a function. X here is the independent variable and y is the dependent variable. So if we sketch the curve of y equal to x squared, most likely we have something of this nature, a curve. And this is your y-axis and this is your x-axis. We can pick a point, P. At this point, we find the gradient of the curve. The gradient of the curve by drawing the tangent to the curve at point P. We have delta y and delta x as usual. So if we have delta y and delta x, that means the gradient at this point, the gradient at point P is equal to delta y over delta x. And that is the values obtained y2 minus y1 over x2 minus x1. But since the values are not given at that point, we can find the limit of the gradient as delta x approaches a particular number. Maybe the number here, xp. So for it to approach that, we can be able to solve delta y to delta x approaching the value of dy dx. And that will lead us to the term dy dx. So as the value of x approaches the xp at that point, then delta y divided by delta x will approach dy dx. So therefore, we can also establish the fact that the rate of change of a quantity with respect to the other is the dy dx of the function or of the relationship. That is the fundamental principle here. So that will lead us to what we call first principle of differentiation. first principle of differentiation. How do you differentiate using first principle? If you can understand how to differentiate using first principle, then you can solve a lot of problems, okay, using first principle. Let's see how we can solve problems using first principle. With that, we can go ahead and solve other related terms, other related function, different types of function in calculus. Okay, now let's look at first principle. First principle of differentiation. First principles of differentiation. You are given that f of x is equal to x. F of x is equal to x. Differentiate using the first principle. To differentiate this using the first principle, we can assume that this f of x is equal to y. So that means I can say y equal to x. So that means if we have this as a straight line, and we have this as the line representing y equal to x, we can find the gradient function delta y delta x. So the gradient, which is delta y divided by delta x, we approach delta dy over dx as soon as delta x approaches the value of 0. As soon as delta x approaches the value of 0. So that means if we have to solve this, we say that a small change, if there is a small change in y, a small change in y, it will result to a small change in x at this point. Small change. So we can call this delta x and call this delta y. So that means delta y and delta x are the changes we are looking at in the expression. So y plus a small change, let me use this term, small change in y, is equal to x plus a small change in x. We have this expression. That is a gradient function. That's a gradient function. We can make the small change of x, of y, the subject of formula, and that is equal to x plus small change in x subtract y. You recall that y is equal to x from this expression. So if y equal to x, we can now say that small change in y is equal to x plus small change in x subtract y. The y there is equal to x. Now you find that x will cancel out x. X will cancel out x. So small change in y is equal to small change in x. We divide through. Divide both sides. Both sides by small change in x. So when we divide, what we have is delta y divided by delta x is equal to delta x divided by delta x. So delta x cancel delta x, and that will give us 1. That means as delta x, that is small change in x, approaches 0, that means small change in y divided by small change in x, we approach dy dx. Okay? And that means dy dx based on the first principle here is equal to 1. So using the first principle, we have been able to solve that or find that delta y over delta x or dy dx of this function is equal to 1 using the first principle. So we can look at other examples. Let's look at another example. Solve using first principle, y equal to s squared. Y equal to s squared. In this case, let us assume, for those of us that cannot write small change in x or small change in y, I will advise to use small change in x equal to delta x, and small change in y is equal to delta y. So if you have to solve this equation or this expression or function using first principle, let's go along together. So we have y equal to s squared. So when we introduce the small change in y, that means y plus delta y is equal to x plus delta x all squared. Simplify this. You can take this one, make it subject of formula. Delta y is equal to x plus delta x all squared. Subtract y. Okay? Remember that your y equal to s squared. So we have delta y is equal to, you can expand this. We have x squared plus 2x delta x plus delta x all squared minus y. Y is s squared. You find that s squared and s squared here will cancel out. They will cancel out. So delta y is equal to 2x delta x plus delta x squared. This is the gradient function. So using this gradient function, we divide by delta x. So when we divide by delta x, we have delta y divided by delta x is equal to 2x delta x divided by delta x plus delta x squared divided by delta x. This cancelled this cancelled one of these. So we have delta y divided by delta x is equal to 2x plus delta x. And as delta, if you find the limit of this is when delta x approaches 0. So when delta x approaches 0, delta y divided by delta x will approach dy over dx. So as it approaches dy over dx, we say that dy over dx is equal to 2x plus 0. That means dy dx is equal to 2x using the first principle. So with this, we know that we can use first principle to solve this kind of problem. So I believe that we can solve other problems using first principle of differentiation. So these are more examples we can solve differential questions or function using first principle. You can go through the example. They are similar to what we have there. But I would like us to have these other examples and as practice work for your own good, so you can solve the following. We have the first one. Using first principle, you can solve this whole problem. 1 over x, 3, 1 over square root of x, 4, 2x squared plus 4x minus 1, and 5, 1 over x plus 1. Using first principle, I would like us to solve this. And also, you also solve these ones as well. If evaluates 1, limits x approaches 1, x to the power of 3 minus 1 over x minus 1. 2, limits x approaches half, x squared plus 1 divided by x squared plus x plus 1. And the third one is limits x approaches 0 with x plus 1 all squared. Okay, 1 all squared. Okay, that is 1 all squared, not 1 all squared. Okay, sorry for that. 1 all squared. So this is 1 here. So this is 1 all squared divided by s cubed minus 2x plus 5. So we can solve these examples as practice work. So I will expect us to practice them as we come to the end of this class today. So in subsequent classes, we are going to look at the application and the other aspects of differentiation using the formula method. We are going to look at the quotient rule and the product rule, and also we look at the chain rule of solving calculus, that is differentiation. So thank you for listening. Remain blessed.